Okay, here we go with chapter 12, amino acids, proteins, and enzymes. So we're going to start with section 12.1, which is amino acid structure and classification. All right, so let's get started with the structure of amino acids. And the kind of amino acids we're interested in our class are going to be alpha amino acids. So an alpha amino acid is an organic compound containing both an amino group and a carboxylate group, with the amino group attached to the carbon next to the carboxylate group. And then there's a note here about proline, which differs slightly from the general formula of an amino acid because the amino group and the R group are part of a ring. But let's take a look at the structure inside this box here on the left-hand side, where we have the condensed structure of our alpha amino acid. So you notice that you have the carbonyl here from your carboxylate group, and the carbon that's attached directly to it, we call it the alpha carbon. So this is our alpha carbon. You can put an alpha here like this. And you'll notice that alpha amino acid. So attached to our alpha carbon, we have the amino group, and then we also have the carboxyl group. Okay, and the carboxyl group is the part that comes from a carboxylic acid, right? You can imagine if you had a proton here, it would be in a carboxylic acid. So the carboxyl group is the acid, the amino group is the amine, obviously. And in this case, we have an R group where it says side chain different for each amino acid. Well, we're going to take a look at all the different side chains for the 20 naturally occurring amino acids, but there's a couple things you should remember right away. The first thing is that if the R group does happen to be hydrogen, so if the R group is hydrogen, then this carbon, meaning the alpha carbon, would not be attached to four different groups because then it would be attached to hydrogen. So in that case, it wouldn't be a stereocenter. And again, if the R is H, you should memorize that that is glycine. Okay, the name of that amino acid is glycine. It's the only alpha amino acid that does not have a stereocenter in it. Now you can see the skeletal structure here is shown on the right where we leave out the carbons. And we leave out the hydrogen on the alpha carbon as well. And we're going to get some practice drawing that in just a little bit. But just to point out what the slide here is saying about proline. So I've already gone over glycine where the R group is a hydrogen. Well, you can see that in proline, your R group is CH2, 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 but it is tethered to the amino group. And so in proline is very unique in that it has a ring, okay? And so this is proline. Now, in this class, I don't demand or ask that you memorize the structures of all the naturally occurring amino acids, but the more of them that you do know, the easier the chapter does become. Now, as I was saying, there are 20 common naturally occurring amino acids that make up proteins. They're alpha amino acids. So again, we have our carbonyl. The carbon next to that is our alpha carbon. And on the alpha carbon, we have our carboxylate, we have our amino group, and then we also have our R group. So each amino acid is differentiated by its characteristic side chain, abbreviated generically with an R. And like I told you, if R is a hydrogen, that would be glycine, okay? So glycine. I can tell you another one, if you have a good memory, if R is a methyl group, if it's a CH3, that's called alanine, all right? And again, I'm going to show you the structures of all the R groups and the names of the associated amino acids in just a little bit. But these side chains contain their own functional groups. Sometimes we have alcohols or amines, aromatics, and those are going to confer individual characteristics to each of the amino acids. So when we look at our amino acids in a few minutes, we're going to see that they're all going to have this part in common, essentially, except for proline, which has the ring. But what's going to set them all apart is their R group, right? And you can see that already with the first two examples I've given you. If R is a hydrogen, it's a glycine. If R is a methyl, it's an alanine. And so we're going to look at all the different R groups. And you want to remember that when we see a wedge like the one that is shown right here, remember this dark black triangle here, this long drawn out triangle, if you will, that is a wedge. And that wedged bond indicates that the bond is coming out of the plane of the screen or the page from you. And this is the favored stereoisomer for the vast majority of naturally occurring amino acids. So just remember, there are 20 common naturally occurring amino acids. Does that mean there are only 20 amino acids? Of course not. Okay, there are other amino acids. However, we're going to focus on the 20 common naturally occurring amino acids. Example 12.1, draw the skeletal structure of the amino acid for valine. So this is valine shown here. All right. And draw the skeletal structure since valine is shown here in its condensed form. Well, if we remember, we're going to start with our alpha carbon and then attach to our alpha carbon. So I'll just label this as our alpha carbon, this one here. We're going to have our carboxylate group. All right. Then we're going to have our amino group, NH3 plus. And then we're going to have our R group, which in this case is this isopropyl group. And so we'll put it like that. And so there is our skeletal structure of valine. Now, if you remember in the carbohydrates chapter, we used Fisher projections to represent carbohydrates. And so we're going to use Fisher projections sometimes to represent amino acids. So if you just follow along with me here, the general formula for the 20 amino acids can also be represented as a Fisher projection with the alpha carbon at the intersection of the Fisher projection shown explicitly. And so here we have our alpha carbon, and here we have our alpha carbon. Now, with the exception of glycine, which I told you where the R group is a hydrogen, there are four different types of groups, or sorry, there are four different groups. Now, with the exception of glycine, where I told you that the R group is a hydrogen, there are four different groups attached to the alpha carbon. And as a result, 19 of the 20 amino acids can exist as two stereoisomers, which are most commonly referred to as the DNL forms. Now, when we looked at carbohydrates, it was the D sugars that predominated in nature. However, when it comes to amino acids, it's the L form of amino acids that predominate in natural systems. And so we're going to be focusing on L amino acids. We have our carboxyl group up at the top. We have our amino group on the left. And so when it comes to the 20 naturally occurring amino acids, we actually classify them based off of the polarity of their side chains. Now remember, side chain is just another way of saying the R group, okay? So we look at the R group, and based off of the R group, we'll put them in one of these four categories. And so let's take a look at these categories. The first one is neutral and nonpolar. The next one is neutral and polar. Then we have acidic and polar and basic and polar. So acidic side chains are going to contain some kind of additional carboxylate group. So if you see an extra carboxylate group in your amino acid, it means it's acidic. Whereas the basic side chains are going to contain some kind of additional amino group, something maybe like that, okay, in the molecule. And when it comes to amino acids, just to make representing them quick or rapid, we have both three-letter and one-letter abbreviations that we use to represent them. Okay, so let's start with the neutral and nonpolar amino acids. So again, none of these have a charge. Um, None of these R groups have a charge, rather, and none of them are polar. So we're going to start with glycine, where R group is a hydrogen. So again, notice that what they're showing here, this is the alpha carbon. So when R is equal to an H, it's a glycine. We use GLY or G. Then if we have a methyl group, as I told you before, then we have alanine, ALA, the letter A. Next one is if we have an isopropyl group. So you probably remember or recognize what's in the box here. This is isopropyl group here. That's a valine. Kind of looks like the letter V upside down like that. So valine V. Then we have leucine, and you probably recognize this is an isobutyl group. It's shown here in leucine, Leul. If we move back down, and I'm really zooming in here, then we have isoleucine, and that's actually a sec-butyl. That's a sec-butyl group. And so we have leucine, which has an isobutyl. Then we have isoleucine, which is a sec-butyl. So isoleucine, we use the letter I or ILE. Then we have phenylalanine, right? F for phenylalanine is the one-letter abbreviation, and PHE is the three-letter abbreviation. Phenylalanine has a CH2 group followed by an aromatic ring. Then we have proline, and we went over that, how The R group in proline is tethered or tied through to the amino group. So there's a ring in proline, and that's unique. It's the only amino acid that has a ring that attaches the alpha carbon to the amino group. And then finally, we have methionine. So this is the only one in this slide that has a sulfur in it. So methionine, MET, or M, and you can see we have CH2, CH2, S, CH3. So what do all these neutral nonpolar side chains have in common? Everything that's highlighted in green. First of all, none of them have any charges, and so they're neutral. And none of them have any polar functional groups in them, and so they are neutral in nonpolar side chains. Okay, moving on to neutral, no charge, but polar side chains on amino acids. The first one we have up here is serine, and you can see why this is polar. It's got an OH group in it, right? It's got a hydroxyl group, which is capable of hydrogen bonding, so serine, SERS. Then we have threonine, and again, you can see we have an OH in here, which is capable of exerting dipole-dipole forces and hydrogen bonding. So threonine, THR. Then we go to tyrosine. And if you're looking at this and saying, well, if I didn't have this here, it would be phenylalanine. You're right. So tyrosine is just a phenylalanine that has a hydroxy down here on this carbon. We use Y for tyrosine, TYR. Then we have tryptophan. And if you're looking at that and saying, wow, that's pretty interesting. Yep. Tryptophan. This ring system here, you don't have to know this. This is called an indole. It's neither here nor there. But you can see that in tryptophan, we have the NH bond like this, which renders it polar. If we go back down to the bottom corner here, we have cysteine, so which has the SH bond here, so we call that a thiol. Then we have asparagine and glutamine. So asparagine and glutamine, and the only difference between the two is one CH2 group. You'll notice that asparagine, ASN, goes CH2 carbonyl, so CH2 carbonyl NH2, whereas glutamine goes CH2 carbonyl NH2. And so that's the only difference between the two. So glutamine, we use the one-letter abbreviation Q, the three-letter abbreviation GLN. So what do all these neutral and polar amino acids have in common? Well, first of all, they're neutral. They don't have any charge, but then they all have some kind of polar bond in them that enables them to participate in, dipole-dipole forces and largely hydrogen bonding. Not all of them, but mostly. Then we can squeeze both the basic and acidic amino acids on the same slide because there's only two acidic polar side chains. They both have extra carboxylates here in aspartic acid and glutamic acid. So aspartic acid is ASPD, glutamate is GLU or E, and again, the only difference is one CH2 group. Then for everything that's basic, you have a nitrogen with a positive charge on the side chain somewhere, and we have histidine, lysine, and arginine, and their abbreviations are HK and R, respectively. Now, you notice I didn't go over every three-letter abbreviation and one letter abbreviation here in detail. And again, that's because you don't have to have them all memorized at this point. You should just be able to recognize the three basic groups: neutral and nonpolar, neutral and polar, and basic and acidic amino acids. All right, for each of the following amino acids, use table 12.1 to identify a structural feature of the side chain that places the amino acid in that category. So the first one is threonine, and they're telling us that threonine is neutral and polar. And so what I'm going to use in this video is I'm actually going to use bond line structures. So for our threonine, we have something that looks like this. So we have something that looks like this. This would be our threonine. And so why would this be neutral and polar? Well, first of all, the R group, the side chain, is neutral, but it also has an OH bond in it, which is capable of hydrogen bonding, which renders it polar. Next, we have lysine. So it says here lysine is basic. And again, I'm going to use bond line structures. I forgot my positive charge here. Anyhow, so for lysine, we have NH 3. Then we have our carboxyl group over here. So we have 1, 2, 3, 4. 1, 2, 3, 4 carbons. Then we have NH3 plus in our lysine. Okay, in our lysine. And so it's going to be this portion here, the NH3 group, that makes that R group basic and polar. Next, we have valine, and we already did valine, or we already looked at it quickly. So I'm just going to scribble this down very quickly. It's neutral and nonpolar. Why? Because the R group is just a simple isopropyl group. So this isopropyl group here, it's not charged, it's nonpolar. And the last one is glutamate. And glutamate is going to look something like this. So we have our NH3. We have our carboxyl group here. Then we have 1, 2 carbons. So 1, 2. Then we have our carboxylate like this. And so this is the part of the molecule that's going to make it acidic and polar. And so there we go with our threonine, lysine, valine, and glutamate.